Hello everyone, and welcome to today's video on roots of polynomials in the exam questions series. This topic links in really nicely with complex numbers. It's also a really cool algebraic technique. Since I think different teachers probably use slightly different notation, I'm going to start by quickly introducing the notation I'm going to use throughout the video, and then whiz through the top tips before moving on to some questions. Just a quick note, from this point onwards in the series I've decided to actually try the questions myself before doing the video, so you don't have to sit through agonising pauses as I type into my calculator, which should improve video length a little, although I'd still recommend trying the questions out yourself first, as I tend to pick challenging ones for the video. Please let me know in the comments down below what video length you'd like me to aim for in future. So, notation. For Vieta's formulae, which is just the formulae that you use for roots of polynomials, for the sum of roots, alpha plus beta plus gamma, I will call that the sum of the alphas, and for the sum of the product pairs, alpha beta plus beta gamma plus alpha gamma, alpha gamma. Of course, this is just for a cubic, but the same pattern will apply to quadratics and quartics as well. And the highest order you can get is a quartic, I believe, for Edexcel. And this is, I'll just put the sum of the alpha beta gammas, but it really is just alpha beta gamma. So that's the notation. I'll leave that up at the top. And top tips then. So the first one is to remember where the negative signs appear in the roots of polynomials formulae, because, well, you'll see down below, but when we have cubics and quartics, then the sum of the alphas and some of the alphas will always be negative of the coefficient, and you need to remember that alternating pattern. Secondly, write out the expressions carefully when you're expanding. For example, when you're doing a linear transformation of roots, consider all the terms, and remember that a complex root always appears with its conjugate. That's always a useful thing to remember. And in my opinion as well, for many linear transformations, the substitution method is the quickest and easiest. So I know there are alternatives, but I would always opt for the substitution method. Not only is it quicker, but you're also less likely to make a mistake. So the first question, just a relatively easy one to introduce the notation a little bit more. So the roots of the equation ax cubed plus bx squared plus cx plus d equals 0 are 1 plus or minus 2i and 2. We need to find integer values for a, b, c, and d. So the minus sum of the alphas is going to be b divided by a, and the sum of the alpha betas is going to be c divided by a, and the sum of the alpha beta gammas, or just alpha times beta times gamma, is d over a, minus the sum of the alpha beta gammas. And so for the sum of the alphas, we're just going to add up our three roots over here. So if we do that, 1 minus 2i, add 1 plus 2i, add 2, gives you the sum of the alphas is 4. So b over a is minus 4. That's the first thing. And secondly, this one gives us the sum of the alpha betas. If we add up the sum of the product pairs, so that's going to be 1 minus 2i times 1 plus 2i, add 1 plus 2i times 2, add 1 minus 2i times 2. That's going to give you an answer of 9. And so c over a is 9. And if we multiply all of the roots together, then we get, so 1 minus 2i times 1 plus 2i times 2 is minus 10. So the sum of the alpha beta gammas is 10. And so d over a is going to be minus 10. So given those, and we need to find integer values for a, b, c, and d. So we can say A is 1, B is -4, C is 9, and D is -10. And that's the answer to the first question. So I've just multiplied, because we know what B over A, C over A, and D over A are, for integer values, I've just said let A equal 1. But of course, any multiple of this equation would also work. Moving on to the second question. The cubic equation 2x cubed minus 10x squared plus 8x minus k equals 0 has a root at x equals 3 minus I. And having been told this, we know that there will also be a root at 3 plus I, because complex roots always appear with their conjugates. And we need to find then the other root and the value of k. So the sum of the alphas, if we add up all three roots, is going to be, minus the sum of the alphas will be minus 10 over 2. So the sum of the alphas is 5. So 3 plus I add 3 minus I, add alpha, we'll call that the other root, is 5, which gives us alpha is -1. So that's the other root. And in order to find the value of k, I'm just going to substitute in -1 into the above, and we know that we want it to equal 0, so that'll tell us what k is. So we have 2 minus 1 cubed minus 10 minus 1 squared plus 8 minus 1 minus k equals 0. So we have, expanding that out, minus 20 minus k equals 0, and k equals minus 20. And those are just two answers to that question. Moving on to the next one. The cubic equation x cubed minus 14x squared plus 56x minus 64 equals 0 has roots alpha, k alpha, and k squared alpha. I actually did this one from the textbook. It's not a past paper question, but I did think it was quite a nice one. So I'm just going to apply the same rules as before to start with. So alpha, or the sum of the alphas, minus the sum of the alphas is minus 14. And a here is 1. There's a hidden 1 in front of the x cubed. So minus the sum of the alphas is just minus 14. Sum of the alphas is 14. And so if we add up alpha plus k alpha plus k squared alpha, we will get 14. And if we do the sum of the product pairs, which is alpha, k alpha, well, let me actually write that out first. So the sum of the product pairs is 56. So alpha, k alpha plus k alpha, k squared alpha plus alpha, k squared alpha is 56. And expanding that out, we have k alpha squared plus k cubed alpha squared plus k squared alpha squared, which is alpha squared k plus k squared plus k cubed. That's the sum of the product pairs. And then I'm just going to come back up here to look at the sum of the alpha beta gammas. So the minus sum of alpha beta gammas, so the product of all the roots, is going to be minus 64. So that tells us that alpha times k alpha times k squared alpha is positive 64. Which is the same as alpha cubed, k cubed equals 64. And if we cube root both sides, then we get alpha k equals the cube root of 64, which is 4. And here, and this is probably one of the hardest steps of the problem, with this, I'm going to rearrange this to get alpha in terms of k. And then this is a rather neat form of simultaneous equation, which I can then use, or it's an equation which I can use to form simultaneous equations by substitution in order to find the values of alpha and k. So using alpha equals 4 over k, we can then substitute that back into the equation for the sum of roots. So we have 4 over k plus k times 4 over k is just going to be 4. And k squared times 4 over k is going to be 4k equals 14. Multiplying both sides by k, we get 4 plus 4k plus 4k squared equals 14k. And 4k squared minus 10k plus 4 equals 0. And as a quadratic, our two solutions for k, if we solve it using the quadratic formula or our calculator, we get that k equals 2 or a half. So if k is 2, then using our formula earlier, alpha equals 4 over k. Alpha equals 4 over 2, which is 2. And if k equals a half, alpha equals 4 over a half, which is 8. And those are our two sets of possible solutions. So there are two sets of solutions for k and alpha in this question, and they are those. So moving on to the next question, we've been told the cubic equation ax cubed plus bx squared minus 19x minus b equals 0, where a and b are constants, has roots alpha, beta, and gamma. So there's really not much information here yet, but we know that's the only number we have, minus 19x. The cubic equation w cubed minus 9w squared minus 97w plus c equals 0, so we have a little bit more information there already, where c is a constant, has roots 4 alpha minus 1, 4 beta minus 1, and 4 gamma minus 1. And we need to determine the value of a, b, and c. So first of all, what I'm going to do, and this is the substitution method, I'm going to express w in terms of x, so i.e. 4 alpha minus 1 in terms of alpha. So w is just 4x minus 1. And then, using the binomial expansion, I'm going to substitute 4x minus 1 for w in the second cubic equation here. So we have 4x minus 1 cubed minus 9, 4x minus 1 squared minus 97, 4x minus 1 plus c equals 0. And if we binomial expand that, which I'll leave this bit out of the video, again, one of the bits where I'm trying to make it slightly shorter. So if you binomial expand that, you'll get 64x cubed minus 192x squared minus 304x plus 87 plus c equals 0. And then we know that this equation, and the initial equation which they gave us in the question, the first one, both of those are in terms of x, and they both equal 0, so therefore they're both equivalent. And if we compare, looking at the 19, minus 19x and minus 304x, that can tell us what the multiple of this equation is, so to speak. So in the first one, where we had ax cubed minus 19x, we're going to express the sum of the alpha betas in both of them. So we have minus 304 from here, divided by 64, always remember to divide by the initial coefficient of the equation, is equal to, and then going back to our first equation, we know that that's going to be minus 19 divided by a, because the two expressions are equivalent. So the minus signs will then cancel, and this leaves us with an equation which we can solve for a, and we get that a is 4. And that's the first value now found. And then from there, we can look at the other values which we have. So we have minus 192 divided by 64 equals b over a. And we know what a is now, so we can simply solve for b. So b over a equals minus 192 divided by 64, which is just minus 3. And a is 4, so we have b over 4 equals minus 3, so b equals minus 12. And that's the second value that we were after. And then all we need to do now is find c. So exactly the same process. 87 plus c divided by 64 equals, and in the initial equation we had minus b, so equals minus b over a. And we know what that is now, so 87 plus c over 64 equals 12, so minus 12, which is plus 12, over 4, which is 3. And multiplying both sides by 3, 87 plus c multiplying both sides by 64, 87 plus c equals 192, and this gives us c equals 105. And those are the solutions to that question. So I've started by using substitution there, and then we've just solved one by one, working with the information which we had to find the values of a, b, and c. Moving on to the next one. So f of z is z to the 4 plus az cubed plus bz squared plus cz plus d, where a, b, c, and d are real constants. And they have roots z1, z2, z3, and z4. When plotted on an Argand diagram, the points representing these roots form the vertices of a square, with one vertex in each quadrant. Given that one of the roots, z1, is 2 plus 3i, determine the values of a, b, c, and d. So thinking about our Argand diagram, so I'll draw a quick sketch here. We have 2 plus 3i here, and we know that its complex conjugate 2 minus 3i is also going to be a root. And since they form the vertices of a square, we can see this distance here is 6. So we need to go horizontally 6 in this direction to here and here, this one because of the complex conjugate idea, to find the other roots. So listing the roots here, we have 2 plus 3i, 2 minus 3i. The other one is then going to be minus 4 because we're going 6 in that in the horizontal direction. We're not going in the other direction. We're going to the left because we're told that one vertex in each quadrant. Minus 4 plus 3i and minus 4 minus 3i. Those are the roots of our equation, which we're then going to work with to find a, b, c, and d. So a is the minus sum of the alphas, which is the sum of roots. So that gives us, if we add up all those roots, we'll end up with minus 4. So a equals 4. The sum of the alphas is minus 4. So sum of the alphas is minus 4, so a is 4. And for the next one, if we do the sum of the product pairs, then there are quite a lot of product pairs, so make sure that you count them all with this quartic. But if you do that, you get that the sum of the alpha betas is 6, and straight away we know that B is 6, no minus sign needed there. And for the final one, we just multiply the roots together. Oh no, sorry, we've got C first. My bad. So the sum of the alpha, beta, gammas, in this case, not multiplying all the roots together, this is a quartic. So it's, in this case, is going to be alpha, beta, gamma plus alpha, gamma, delta plus beta, gamma, delta plus alpha, beta, delta. And a good check when you're listing these out to check that you're not missing any out is that in an expression like this, you need to recognize how many times each needs to appear. So here we've got 4, and the alphas are going to appear in 3 of them, but not in the other one. And that's how you need to make sure that you've got each one appearing 3 times, you know that you haven't missed out any expressions. So if you substitute into the expression I've just given, then the sum of the alpha, beta, gammas is going to be minus 4, and that means that C is minus the sum of the alpha, beta, gammas, which is 4. So C equals 4. And for our last one, finding D, we're just multiplying all 4 roots together, and that gives us a rather large value of 325. Sorry, minus 325. So that tells us that D is, because it's the minus the sum, or minus the, messing up, is going to be positive 325 there. So D is 325. And that's the answer to that question. Moving on to the next one, which is the last one. We're told the cubic equation 3x cubed minus 9x squared plus 6x plus 2 equals 0 has roots alpha, beta, and gamma. And then we need to write down the values of alpha plus beta plus gamma, and then the sum of the alpha betas and the sum of the alpha beta gammas. So quite an easy question to start with. So alpha plus beta plus gamma, which is the sum of the alphas, is, so the sum of the alphas, or the minus the sum of the alphas, is going to be minus 9 over 3. So the sum of the alphas is going to be 3. The sum of the alpha betas, so the sum of the product pairs, is going to be 6 over 3, which is 2. And the product of roots, alpha, beta, gamma, is going to be minus 2 over 3. So that's the answer to the first part of the question, or rather that. And part II is worth 9 marks, so a lot of marks for a roots polynomials question. And looking back at the question, it's a transformation question, but it's quite a hard one because it's not linear. So we have alpha squared, beta squared, and gamma squared as the roots. And they've told us to show that C equals minus 4 over 9. So they've been quite nice to us there, because we know that once we found C equals minus 4 over 9, we're using the right method, and it also sort of validates our answer to part I as well, so that we can be sure when we're using the other answers. So, looking at this then, we have the I think C is the easiest one to start with, because the product of roots here, alpha squared plus alpha squared, beta squared, gamma squared, is just alpha, beta, gamma, all squared. Which is, and we know what alpha, beta, gamma is, we just worked it out, it's minus 2 over 3. So we're doing minus 2 over 3 squared, which is 4 over 9. And we just need to remember to make that minus, because, again, in this case, it's always the negative product of roots, which is the coefficient that we want. So we know that C is going to be minus 4 over 9. And that's good, because that's the first thing which they wanted us to show. And we've got x cubed. There's no coefficient in front of the x cubed here to worry about, which is why we could work out C straight away and not C over such a coefficient. And now for the harder part, because we need to be very careful that we're not missing out any terms when we're coming up with expressions for the sum of product pairs and sum of roots here. So the sum of roots is going to be alpha squared plus beta squared plus gamma squared. And we can express that partly. A nice way to start is noticing that if we do alpha plus beta plus gamma all squared, we will get the terms that we're interested in. However, we're also going to get some other terms. So if we expand out alpha plus beta plus gamma squared, we're going to get alpha squared plus beta squared plus gamma squared. Those are the terms which we're interested in. And then we're also going to get two lots of alpha beta plus beta gamma plus alpha gamma. So essentially what we have here is that alpha squared plus beta squared plus gamma squared, we can write that as the sum of alphas squared minus two lots of the sum of the alpha betas. And just by expanding those terms out there, we've now got alpha squared plus beta squared plus gamma squared in a form that we can easily solve, because we know the sum of the alphas was 3, so this is 3 squared minus 2 times the sum of the alpha betas, which was 2, giving us positive 5, and therefore the sum of product pairs in this case, or B, is just going to be, oh sorry, not B, I didn't mean B, I meant A. A is going to be 5. Minus 5, sorry. I didn't mean the product pairs, I meant the sum of the roots. And for the next one, we just need to find B, which is the hardest one, but it's still alright as long as you're careful not to miss out any terms. So what we're looking for is alpha squared beta squared plus alpha squared gamma squared plus beta squared gamma squared. That's what we're interested in finding, because that is the sum of the product pairs of the new equation. If we square the initial sum of product pairs, so we have alpha, the sum of the alpha betas all squared, then that's alpha beta plus beta gamma plus alpha gamma times itself, which I'll just write out here so that you can see yourself more clearly where the terms are going to come from. If we expand that out, then we get alpha squared beta squared plus beta squared gamma squared plus alpha squared gamma squared. Those are the terms which we were interested in. But then we're also going to get some initial terms. We're going to get two lots of alpha squared beta gamma plus beta squared alpha gamma plus gamma squared alpha beta. And if you expand out this, that is what you're going to get. And so we can re-express that. We rearrange it to get what we want. So alpha squared beta squared plus alpha squared gamma squared plus beta squared gamma squared equals the sum of the alpha betas squared. And here's the neat part. This bit here, if we factor out the alpha beta gamma, which is in each of these terms, then something really nice happens. We get 2 alpha beta gamma, and then in here we just get the sum of the alphas from the initial equation again. And sorry, my apologies, that should be a minus sign, not a plus sign. And substituting in the values which we know, we then have 2 squared minus 2 lots of, and then we have minus 2/3 and 3. So if we calculate that, then we'll get this is 4 plus 4, and then we get b equals 8. And it's just positive 8. We don't need to make it negative because we're looking at the sum of the product pairs here. So that's how I've done that question. We've just used what we know, and we've looked at what happens when we maybe square it, and we've just got lots of additional terms. But you'll always be able to find a nice way in these questions of expressing all of those additional terms in terms of your initial expressions that you started with before the transformation. So that's how you do a hard question relating to related roots. That's the end of the video, so I hope you found it helpful. Some of the questions in here were pretty hard, so well done for having a look at them, especially if you gave them a go, because practice really is the route to success. Next video might not be for about a week, as I'm going to be quite busy this next week with other things, but it's going to be on volumes of revolution next. Anyway, thanks for watching, and I'll see you in the next one. Bye.